Okay, let's dive right in. The universe is just full of these unbelievably violent events. Black holes smashing together, stars exploding, even the aftershock of the Big Bang itself. And every single one of these things sends out ripples in space-time, gravitational waves. So today, we're basically going on a cosmic detective mission. We're hunting for a very specific clue, a faint, constant hum that seems to fill the entire universe. We're going to figure out what it is, where it's coming from, and what it can tell us about, well, the story of everything.
The scientists looking for this signal have a fantastic way of thinking about it. Imagine you're in a super crowded room. It's really easy to pick out one person shouting your name, right? But all the other conversations, they just blend together into this general, indistinct murmur. Well, it turns out the universe is a lot like that room. The shout is a single, powerful event we can clearly detect. But that murmur, that is the cosmic background we're trying to find.
All right, Section 1, the universe's background hum. So our first job as detectives is to really get a handle on the signal we're looking for. This isn't one clean sound, oh no. It's more like a chorus of countless whispers coming at us from every direction, all at once, blending together into a kind of cosmic static. And let's be clear, we've gotten really good at hearing those shouts in the cosmic room. When two huge black holes spiral into each other, they let out this powerful, distinct chirp in gravitational waves that our detectors can pick out no problem. We've actually cataloged dozens of these. Each one is a specific, solvable event. But here's the thing. For every one of those loud shouts we can hear, there are millions, maybe billions, of fainter whispers. These are signals from events that are just too far away or too weak or simply too numerous for us to pick out one by one. They all just overlap and mix together, creating this continuous, incredibly faint signal that's washing over the Earth from all directions all the time.
So this cosmic murmur has a fancy scientific name, of course. It's called the Stochastic Gravitational-Wave Background, or SGWB for short. Now, stochastic just means random. Think of it like the sound of rain. You can't hear a single raindrop hitting the ground, right? But you can describe the overall sound of the downpour. That's exactly what we're doing here. And this signal is the mystery at the very heart of our investigation.
Okay, so every good detective story needs a list of suspects. What in the cosmos could possibly be creating this constant hum? Who or what is responsible? Well, our suspects fall into two main categories, from two totally different periods of the universe's history.
So our suspects are in two camps. First, you've got your astrophysical sources. Think of these as the ongoing noise of the universe today, all those merging black holes and exploding stars we talked about. But then you have the cosmological sources. These are way more ancient, way more mysterious. These are primordial echoes from the fiery birth of the universe itself, a sound that's been traveling through space-time for almost 14 billion years just to reach us.
So let's take a closer look at our astrophysical lineup. The prime suspects here are what we call binary systems, basically any pair of massive things locked in a cosmic death spiral. We're talking about everything from the gargantuan supermassive black holes at the centers of galaxies, all the way down to countless pairs of smaller black holes and neutron stars. Each one is contributing its own faint whisper to that background hum.
And now for the really exotic suspects, the cosmological ones. As you can see here, each of these ancient processes would leave a totally unique fingerprint on the hum. For instance, inflation, that insane expansion just after the Big Bang, that would create a smooth, even background. But something wild like cosmic strings, that would create a really strong and distinct signal. I mean, finding one of these would be like finding a clue from the first fraction of a second of creation. It's mind-blowing.
Now, to catch a signal this faint, this elusive, you need a team of highly specialized detectives. And they're using some of the most sensitive instruments ever built by humankind. This is a truly global effort, a planetary-scale detective agency.
And this really gets to the heart of their strategy. It's brilliant. If you're trying to hear a tiny hum in a really loud room, what do? You use both your ears. Your brain can tell the difference between the hum and the random noise, because the hum is correlated. It hits both ears at pretty much the same time. Well, our cosmic detectives do the exact same thing, but with detectors thousands of kilometers apart. They're looking for a correlated signal that's buried deep in the random, uncorrelated noise of each individual instrument.
So the first team uses these enormous L-shaped laser detectors on the ground. You've probably heard of them. The LIGO detectors in the US, Virgo in Italy, and Kagra in Japan. They're built to listen for high-frequency gravitational waves, like from regular-sized black holes merging. And together, they form this incredible global listening network. And having a global network is absolutely critical. Just look at these maps. They show the field of view for different pairs of detectors. See how they're sensitive to totally different parts of the sky? By combining the data from all of them, our detective agency can basically scan the entire sky for this background hum all at once.
But there's a second team of detectives on the case, and they're working on a completely different frequency with a completely different method. They're not building detectors here on Earth. No, they're using dead stars scattered all across our galaxy as their instrument.
So here's how this crazy idea works. Pulsars are like cosmic lighthouses. They're spinning with this unbelievable regularity, sending out beams of radio waves. So step 1, scientists monitor these pulses with incredible precision. The theory goes that a passing gravitational wave will gently stretch and squeeze the space between us and the pulsar, which makes those pulses arrive just a tiny fraction of a second early or late. So by looking for a very specific, correlated pattern of these delays across dozens of pulsars, they can actually detect the background hum. It's genius!
And the key here, the really important part, is that they aren't just looking for any pattern. They're looking for a very specific smoking gun. It's a unique signature that Einstein's theory predicted decades ago. This pattern is called the Hellings-Downs curve, and finding it would be the undeniable proof. The thing that tells them what they're seeing is truly from gravitational waves and not just some other weird noise.
Okay, so we've got our mystery, we've got our suspects, and we've got our detectives. This investigation has been going on for years. So what's the verdict? What evidence have they actually found? Are there any real clues pointing to a detection?
Well, first, just a little reality check on how incredibly difficult this is. We know from looking at the afterglow of the Big Bang that the total energy in this background hum can't be more than about 1/1,000,000th of the total energy in the universe. I mean, the signal is unbelievably, ridiculously faint. We are looking for something truly, truly tiny. And yet, there's a really tantalizing clue. The Pulsar Timing detectives, they've found something. Several different teams, all working independently, have reported seeing a common noise process across many of the pulsars they're watching. And it has the right characteristics, it has the right sound, to be the very first hint of the gravitational wave background.
This is the million-dollar question in all of astrophysics right now. Have they actually found it? They've definitely heard a common hum, but they haven't yet found that definitive smoking gun, that Hellings-Downs correlation pattern, that would just seal the deal. They are so close, you can feel it, but the case isn't quite closed yet.
So what's the big deal, you might be wondering? Why we're pouring decades of effort and building these incredible experiments just to hear a faint hum? Well, because as we're about to see, cracking this case wouldn't just be interesting. It would be one of the single biggest scientific discoveries of this century.
I mean, actually detecting and understanding this background hum wouldn't just be one discovery. It would open up entirely new fields of science. A cosmological background would let us literally see the universe just moments after it was born, testing wild ideas like conflation and cosmic strings. An astrophysical background, that would give us a complete census of every black hole merger that's ever happened. It is a completely new way to read the universe's entire history.
For over 13 billion years, the universe has been humming with the echoes of its own creation, its own evolution. It's a story written into the very fabric of space-time itself. The clues are piling up, our instruments are getting better and better, and for the first time in all of human history, it really feels like we're finally learning how to listen.